Good morning. As I already confessed, I didn't finish marking your quizzes. Yeah, we were saying you can just self-evaluate, give me a grade, let me know, I'll put it on Moodle. So today we're gonna do chapter 7. We already did 6. 6 was an applications chapter. Those applications chapters are the ones that we kind of do stuff in Excel and just kind of poke around and yeah. So chapter 7 and chapter 8, we're doing regression. Now, regression, I feel like I might have mentioned it already, but regression is just a fancy word for line of best fit. In fact, the linear regression is what makes it a line. Right? And the line of best fit is usually, we're kind of comfortable with the line of best fit. You've probably seen it before, maybe even made one, that kind of thing. But a line has what format? Let's see here. A line, y equals mx plus b might be familiar. Right? We need a slope and we need a y-intercept, right? And so for us, we're going to kind of evolve a little bit, and we're gonna be making a y hat equals beta naught plus beta 1 times x. Okay. Same thing. It's just the slope and the x just kind of got shifted around. And so, but it stays the same. Y hat, so y with a hat on it indicates that it's a predicted value. Okay. So it's the predicted value of y. Is the predicted value of y. Oops. Which kind of nudges us toward the goal of regression, which is to predict other values of y, unseen values of y, right? So we collect a sample, and then our ultimate goal is to model that behavior with a straight line. And then we're going to try to predict values of y. Okay. This beta naught, so this is a beta. Beta naught, oops, I almost wrote it with a beta. Beta, Greek letter beta. Oh, hiding behind, I can't see you there. Let's close it. The air is so noisy out there. So this is a beta, and the subscript 0, we're going to, have you guys used a naught, a beta, or a subscript 0 before in your other classes? Maybe sometimes, yeah. So the subscript 0 is a naught, so a null. So naught or null. Okay. And so beta naught is going to be the y-intercept. And then beta 1 is attached to the x. Whatever's attached to the x is the slope. And so beta 1 is the slope. First thing we want to do when we look at a relationship, or when we look at a scatter plot, oh, dang it. I wanted to finish dissecting this thing. This header. Everything's in the header. I take it back. We're not looking at a scatter plot yet. So then, what color haven't I used? I'll use pink again with a single predictor. Sometimes we call this simple linear regression. Okay? And so the predictor in this case is going to be your x. Okay? So it's going to be the explanatory variable. But in a regression sense, we usually call them predictors, right? Because remembering that the goal is to predict y, right? And the predictor helps us do that. Okay? And so here, a predictor is the explanatory variable. We've seen the explanatory variable before, right? And so on our scatter plot, right, we're gonna have our y on our y-axis, okay? And we can call this the response variable or the outcome, right? It's the thing we want to predict against x, which is the explanatory variable or the predictor. Okay. So we try to use the predictors and incorporate the predictors to try to predict y. Okay. And so, okay, so there's, like I said, a lot of information just in the header, right, that we kind of need to dissect and pull apart. And just like we've seen before, right, these betas, any Greek letters, they come from the population. So ultimately what we're trying to learn about is population behavior, right? But in our sample, right, we're going to have a sample version of this line. Okay? And so y hat equals beta naught plus beta 1x. This is the population model, which we are trying to estimate with the sample, which we are trying to estimate with our sample. Which means that we're going to have a little brother situation, a sample version of this line. Okay? If we're using betas, we're going to use just lowercase b's, right? I guess you could use uppercase. What? Crazy. I'll never. B naught plus B1 times X is going to be the sample line of best fit. Okay? So this becomes our line of best fit from the sample. Okay? We only ever have sample information, right? And so we'll be able to fit a line of best fit to our sample, and then that's our best guess at what our population might look like, right? And because you've seen confidence intervals, sort of, right, then you know that, okay, we've got this estimate, but there's going to be error bounds all around this estimate, right? But we're trying to get at what the population might look like. Okay. And so one of the first things that you want to look at when you're making a scatter plot, or when you've made a scatter plot, is you want to be able to describe the relationship. Okay. And we did it a little bit, bless you, like something like that. Okay. And so given a scatter plot, we need to be able to describe the relationship. And much like a histogram, when we're describing the relationship, there are three things, again, that we need to talk about. Okay? So we need to discuss three things. First thing is whether it's a linear relationship or not. And when I say linear, I just mean, does it look like a straight line, right? Does a straight line reasonably model this thing? Okay? And just like the normal distribution, if you can kind of talk yourself into, yeah, a straight line would work, right? Then that's cool, because it makes your analyses a lot easier. Okay? You want to be careful. There's kind of different layers to that. But for us, we're going to be looking at linear relationships. Okay? And so I guess I could call it the shape. It's really, but we're going to talk about linear versus non-linear, right? If we're about to fit a line of best fit, then a line should probably do a good job of describing the overall behavior. Okay? Then we want to talk about the strength of this relationship. Okay? And so this here, I would consider a strong relationship. All these points kind of follow the same pattern. I see this distinct pattern. Okay? And we can have strong nonlinear relationships, as we'll see, but here I've got a linear strong relationship. And so here the strength, oops. Strong versus weak. There are different kind of levels that we could add to this. We could call it moderately strong, but just as a rule of thumb, I'm going to call it strong as soon as you see a pattern, right? If the pattern is kind of hard to detect, but you still kind of could convince yourself of a pattern, I would call it maybe moderately strong or something like that. Add a modifier. But if you can see a pattern, it is considered strong. Right? Or moderately strong. You can kind of describe it however you want. The thing about a weak relationship is that you wouldn't include a weak relationship in your analyses, right? And so a weak relationship would look like what? A weak relationship would look like something like this. Now, the problem with this relationship here is I could draw a line of best fit like this if I wanted to, or I could draw it like this. If I let it draw itself, it would probably look like this, right? And so I'm not able to properly model this relationship, right? And so that's why we don't usually talk about weak relationships, and we don't really analyze them. We don't usually analyze weak relationships. Just because it doesn't, you can fit a line of best fit, but especially if we're looking at this horizontal line here, if I'm using the line to predict values of y, right? I put in a low value of X, I get this middle point Y. I put in a high value of X, I get the same point of Y. It doesn't tell me anything, right? And so that's why we don't. I'm kind of skirting around the fact that if you are working on a huge research project and you've collected all this data and you come upon a relationship that you thought was going to be kind of a heavy hitter in your report, and then it's weak, you would probably still include it in your report, right? And just kind of talk about, okay, well, it was a weak relationship, and that's unfortunate. I'll need more monies so I can collect more data. You always want more monies. But as soon as you can see a pattern, right, just kind of talk yourself into a pattern, I would call it strong or some level of strong. Third thing is the direction. It can be either positive or negative. A positive relationship is going to look something like this, right? And if you're starting on the left-hand side and moving to the right, it's going up, 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 right? Versus a negative relationship. If you're starting in the left and you're moving over to the right, it's going down, right? I put these arrows on here. You don't put those arrows on, right? I just want to show you where they're going. And so the direction tells you about the relationship, right? If X is increasing, Y is increasing, right? So that means that they're increasing together if you have a positive relationship. Whereas kind of more interesting, I think, sometimes is if X is increasing, then Y is decreasing, right? Okay. So that's just by eye, right? And so, of course, there's a numerical measure of the strength and direction of a linear relationship, and that's the correlation. You might have encountered, maybe. I'm trying to remember, did I show you guys that spurious correlation website? I did, right? Yeah. So we have talked about correlation, but correlation technically is a numerical measure. A numerical measure of the strength and direction of a linear relationship. So it has to be linear. That's important. We will always be able to get software to calculate the correlation, right? But it has to be linear for it to make sense and for us to be able to interpret it. And so correlation is denoted by a lowercase r. Sometimes an uppercase r, but I'm glad to see in this textbook, she came to her senses and is using a lowercase r like the rest of us. In an old textbook, she was using a capital R, and it threw me for a loop. I don't like that. So the correlation is going to be a number between -1 and 1. So the correlation is going to go between, has to be between -1 and 1. Which puts, I'll put 0 in the middle here. And so this is something that, yeah, of course, we have a formula that we can use, but usually we would just use software to calculate the correlation, or I would give it to you, right? And so I'm not going to make you do crazy calculations by hand, But for this section, you'll probably want to have a calculator for the next quiz, just because it might be nice to be able to calculate some things. Right? But I'll warn you again, and I'll bring my bag o calculators. Okay, so just as a guide, if the correlation is a numerical measure of the strength and the direction of a linear relationship, then how about reasonably the negative values tell me that I have a negative relationship, and the positive values tell me I have a positive relationship? It's a good place to start. All right, so here, this tells me I have a negative relationship, and a positive correlation tells me I have a positive relationship. Seems reasonable enough. So now we need to figure out, okay, well, a correlation of 0 to 1 on the positive scale, well, I don't know. I think it's kind of, maybe it's just obvious to me, but a correlation of 1 is going to look like this, where all your points are on the exact same line. So that's a perfect linear positive relationship. And so kind of roughly around 0.5. I would use 0.5 as just kind of an internal guide. You can be a little bit flexible, but once you hit 0.5, you'll start to see a pattern. And so on this side, I would call it strong. So positive 0.5 to 1, I would call it a relatively strong positive linear relationship. Same thing goes on the negative side, right? From negative 0.5 to negative 1, I would consider this a strong relationship. Making everything kind of hovering around 0. So at a correlation of 0, you would have just no rhyme or reason here. Right? Look like this versus a perfect negative relationship. A negative 1 would be just on a perfect line, which makes this stretch all weak, right? Negative 0.5 to positive 0.5, and doesn't really matter if it's positive or negative, but we'll have these values so that we can kind of look at them. Okay. But isn't that what the slope is doing? I know, that's what you're thinking. Well, it is, but that's because the slope incorporates, so the slope is your B1, the slope incorporates the correlation. Okay? The simplest way to calculate the slope by hand, and so in y hat equals b naught plus b1x, b1 is the slope and b naught is the y-intercept. Usually I just call it the intercept, because we don't usually care about the x-intercept. And so the slope incorporates the correlation. And so in this equation, B1 incorporates the correlation. And so B1 is going to be, I think they have it in this order. S. I'm trying to remember if she writes the R on the, I feel like she does it opposite of me. What I was debating was the difference between writing the R first or last. I like to write it first. I am pretty sure, because I reacted to it, so, writing it last? Are you crazy? I know. So the correlation, that's what's going to tell it if it's positive or negative. Okay? And it also incorporates the strength, right? How quickly are you rising and that kind of thing. And then what are these little guys? That should read S subscript Y. That's the standard deviation of your Y's. Okay? And so here, this is the standard deviation of the Y values, which you would use Excel to calculate or some software, right? And then S subscript X is the standard deviation of your X's. So if you imagine your spreadsheet, you would have it set up like this, right? You've got some X and some Y values, and at some point X, you observe some value of Y, right? And so you've got X1, X2, X3, blah, 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 Y1, Y2, Y3. And these are all just numerical values. Both of these columns are numerical. And so you can find, right, if I kind of take it way back, I just give you these two columns. Can you calculate the standard deviation of X? Yeah, you can. Can you calculate the standard deviation of Y? Yeah, you can, right? And then the correlation function, you need to feed it your X's and Y's together because it's a measurement of the strength and the direction of this relationship. Yeah. I would give you these components, right? On the quiz, for example. The quizzes are where you make most of your marks, so that's why I want to give you a heads up of what to expect. I don't want to make you do Excel under pressure, although it's tempting sometimes. Might be fun. Might not be. Yeah. Forgot. It's like when I'm watching you type stuff, it just never goes well. And if someone watches me type stuff, it's terrible. So the slope kind of bakes in the correlation, so it's built in there. B naught, B0, B naught, whoops. B naught is the y-intercept for the line of best fit. Is the y-intercept for the line of best fit. In the textbook, she goes through and she does a really great job of explaining kind of why we use the formula that we're using. But are you okay if I just give it to you? Okay. B naught is going to be y bar minus B1 times x bar, which means that you have to calculate the slope first before you can plug it into, I'm really hoping I didn't reverse those two. Nah, stay strong. I'm going by memory, so I'm clearly avoiding the formula for the correlation. It's doesn't matter. So here, that's what I wanted to write. Right. So this means we need to calculate the slope first. All right, because we rely on the slope. Another scenario where, of course, if you get the wrong slope, but you follow through, right, I'm not going to penalize you any further, right? As long as you follow through, then that's fine. Okay. Again, in a quiz situation. One of the fun facts is that the line of best fit always goes through the point X bar, Y bar. That's kind of just a fun fact. How about this? An LFF, a little fun fact. The line of best fit will always pass through X bar, Y bar. The average of your X's and the average of your Y's, right? That'll make a point, and your line of best fit will always go through that point. Okay? And again, right, if you just kind of take a step back and think about how your data would be organized, right, you could narrow it down to just the column of X's and a column of Y's, and you could find the average of each of them, the standard deviation of each of them, right, and the correlation of both of them together. And so this fact is what we use, and it uses the point slope form of a line and rearranges, blah, 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 blah. But there it is. Which means that I need to give you 5 pieces of information for you to be able to calculate the slope and the intercept of a line, right? And so here, therefore, we need 5 pieces of information to construct a line. I guess of best fit. You need X bar, whoops. You need the standard deviation of your X's. You need your Y bar. You need your standard deviation of the Y's. And you need the correlation between the two. Okay. So the line of best fit, let's think about this. And can I grab a scatter plot, a pre-made scatter plot? I'm going to. Wow. This is a brush-tailed possum, and from Australia, of course. Can you imagine if we had something cool like that here? And so what they did, I think they captured 104 of these brush-tailed possums, and they made a bunch of measurements, hopefully randomly selected these brush-tailed possums. I don't think so. But can you imagine so many to grab from? Sitting down again. So we've got data on these brush-tailed possums, and among other things, they measured the total length from head to tail and the length of the possum's head. We suspect there might be a relationship there, right? You've got a really long possum with a tiny little head, cute, but probably kind of strange, right? And so you suspect that there's a positive relationship here, right? As your head length increases, hopefully your body length increases as well if you're a possum. Maybe they don't care. But as we suspected, here, the relationship looks like this. You can just ignore the, well, I'm going to talk about it actually, so you don't have to ignore it even. So now, in this scenario, I would say it's really hard to determine which should be your y value and which should be your x value, right? Do you want to predict the head length, or do you want to predict the total length? In this case, they're telling us we are going to be predicting the head length, right? And so because it's on the y-axis. And so that's our first thing, is we will predict head length. But wait, there's more. Using the total length as a predictor. Bless you. Using the total length as a predictor. Okay. Think about if you had to fit your line of best fit, right? What are you really doing internally? You're trying to probably minimize the distances between all the points and your line of best fit, right? That's what we kind of do internally, right? And so for our line of best fit, let's say maybe we're pretty good fitting lines of best fit by I. But when we imagine a line of best fit, right, then just remember that you're trying to minimize the distances between all the points together, right, as kind of a group from the line, right? So when we visualize a line of best fit, we try to minimize the distances. We try to minimize the distances between all the points and the line. Between all the points and our line. Right? If you think about it this way, if I said, well, obviously our line of best fit is something, well, I'll make it straight at least, is something like this, you would say, really? Right? Because you don't like that. Right? And that's because internally you are trying to minimize those distances. You wouldn't call it that, right? But that is what we're doing, right? And so, and that's what the formulas do as well. And so the most common way, in fact, kind of arguably the only way that we fit lines of best fit is through a least squares regression line. So here, the most common way to fit a line of best fit is by a least, or maybe not, no, I take it back. A least squares regression line. There are other methods, but this is going to be kind of our go-to, and it's kind of the only one. I think it's the only one that Excel does for linear relationships, right? Most software just use the least squares regression line. Now, what does the least squares regression line do? Well, and it's kind of mind-boggling in the way that it goes through, and instead of just kind of blindly drawing a line, it considers a line, right? And then what we do, well, I guess I could use this red guy here, is we calculate all the distances from all the points to the line that I'm proposing. Right? Now, all these distances are going to be called residuals. Where did I write weird? Oh, and our line. Our line. So each point is going to generate a residual, right? And if you think about the term residual, right, it's just a leftover, right? It's a leftover distance from the line to the point. Yeah. And so really, if we're applying the term residual, right, we try to minimize the residuals. Okay. Now, the residual is usually called E for error. Okay. We already saw R is taken, right? R is the correlation. Ah, dang it. Right? I had to figure out a different one, but it is the error term, right? And so we usually use E for the error. And the error of the line is going to be the observed value of Y minus the predicted value of Y. Can I use the shorthand? Y hat. So at each value of X, right, we're going to have, right, so here at this point of X, whatever this is, I have some observed value of Y, right, over on this axis here, maybe here. But I also have some predicted value of Y, right? And so usually how we summarize this is E subscript I is yi minus y hat at I. And the i's are, you can ignore those subscripts if you want, if you don't like them, but it just says that each observation has a residual, right? And so there's an error term for the first data point, the second one, the third one, right? And so the subscript i's just say that all the observations have one. Let me make a note here. This just says all observations have a residual. Residuals can be positive and they can be negative, right? And so if y hat is your predicted value, right, then the y hat is the line. Okay. And so the predicted value, right, if it's above your points, right, then you're subtracting a larger value from a smaller value, making a negative point. And so that means that all these residuals down below the line would be negative, and all the residuals above the line are positive. And as another LFF, little fun fact, they all add to 0, right? And so that leaves us nowhere, right? That's a problem. And so let's say that. A little fun fact, because we're trying to find a line that minimizes all these residuals, just as a fact, the residuals will add to 0. It's just how we've constructed our line. Okay? And so what I mean by it's kind of mind-boggling in the way that, or at least for me, I guess, that it goes through and it just kind of, I imagine it drawing a line calculating all the residuals, and then adjusting the line to minimize all the residuals and to make sure that all the residuals add to 0, right? And that's how it kind of iterates through. We don't need to deal with that. We have formulas that just take that into account, right? But the least squares portion comes into play because if all the residuals add to 0, then if I add them all up, I'm kind of left with nothing, right? In fact, 0. And so then a common way that we've seen already to kind of deal with that, right, is to square the values, right? And so that's what we do with the least squares regression line. We square all the residuals. And so the least squares regression line minimizes the squared residuals. Minimizes the squared residuals. And we've talked about that before, right? The benefit of using a squared value is, of course, it makes negative values positive. That's nice. But it also amplifies large distances, right? And so if you have a residual of, let's say, this point here, very close to the line, right? If I square this distance, it's not really impacted at all. Let's see, there are no outliers on here. But let's say, for example, I had a point out here. What do you think would happen to the line? Uh-oh. It would try to kind of do its best to figure out how to capture that residual, right? And so that's why outliers can be a problem. Okay. I'm going to erase this from here because we'll talk about outliers later, but in terms of the residual, that large residual would be amplified by squaring it, right? And so now, really what we're doing is we're minimizing the squared residuals. Okay. So large residuals are amplified, right? If you consider an error of 1, then the squared residual would be 1 squared, which is 1. No harm, no foul. Let's increase the error term by just 1. So now let's make it 2. Then the residual squared is going to be 2 squared. All of a sudden, from a 1 unit increase here in the residual, I'm seeing a 3 unit increase in my squared residual, right? And so I'm trying to kind of, so the line tries to kind of incorporate that and minimize that, for better or for worse. And so, because I mentioned it, I would say for this reason, is there someone there? Oh, I'm on high alert. Right, outliers can impact your line. Right, it can pull the line towards itself, rendering it kind of useless for the rest of the data, right? If you find yourself in that kind of a pickle, then what I would suggest is you should remove that outlier and kind of refit the line and see if it does a better job. But generally, we try to keep all the data that we can. Okay. What about software? Yes, of course. Software just does all this for us, right? And so let's see here. If you have a scatter plot, one of the things that you can do is you can add a trend line, right? Which you've already done, I know. And you can ask it to just put the line of best fit on your trend line, right? All this is happening in the background, and we don't really need to worry about it. But sometimes we go a little bit end of sentence. Oh, here's the correlation. Let me grab this. Sometimes we go a little bit deeper and we generate some output, right? Instead of just adding the line of best fit to our scatter plot, right? We might want to have some more proper output that I want to show you. Where did I talk about the correlation? Oh, it's been a long time. The correlation, where can I sneak it in here? The formula for the correlation is this. 1 over n minus 1 times the sum of your xi minus x bars divided by the standard deviation of x. We've seen that kind of setup before, right? How far are each of your x's from the mean of x, right? This is a deviation, taking into account the spread. This should feel like a z, right? If you've seen a z or a t, right? That looks similar, right? Standardized distances. And so here, and then we multiply it by the same thing from the y's, right? But you have a correlation command in Excel that you'll use, but it'll do all this, right? And then you multiply them all together and then you add them all up, divided by n minus 1. Bada boom, bada bing. I'm not going to make you do that. That's crazy. We just use the correlation command, or I give it to you. Right. There's so much theory in regression. Well, we offer a whole course on it, right? So Stat 310 is regression. And so if you really like regression, there's a whole whack-load of things that you can do. It's its own kind of field. And so obviously we're going to focus on just the smallest tidbits, but it is a really fun topic. A fun topic? No? Line's a best fit, come on. And so we won't be able to do all the things, of course, but that's kind of the case with everything in this course. So for us, I'm going to really prioritize interpretation. Okay, and so what we need to be able to do is, okay, we understand how the line of best fit is fit roughly, right? Minimize all these distances. Okay? And then we get a slope and an intercept. Okay? We need to be able to interpret those, right? Because that's what you're going to have in your report, and we need to be able to interpret those. But first, I was on the hunt for something here. Kind of went off script, I guess. Oh no. Oh no. I wanted this, but for the possum data. Well, that's okay. I know. I can't believe it. We need to be able to interpret these things, right? That's our most important thing. Okay? And so we need to be able to interpret the slope and y-intercept of a least squares regression line. kind of annoying, but I would say the best starting point is just to memorize these things until they make sense, and then you did it. And maybe that's just because how I do it, right? You can kind of talk yourself into the interpretation of the slope by what? So if we have a line, y hat is b0 plus b1 times x, and we're going to interpret the slope, which is your b1. Right? We could pull in the possums, but let's not. Let's talk about them generically for a little bit. Okay. The slope, we think about how b1 affects your y hat, right? Then if I go from x equals 1 to x equals 2, right, then I have a 1 unit increase in x, right? And the y-intercept is held the same, right? It doesn't change. And so the only change in y hat is going to be from the slope, right? Then I have a slope increase in the predicted value of y. Okay? So it's going to go a little something like this. For each unit increase. I've always thought it would be so fun to write songs about this stuff. I feel like I could do it. Right? Yeah. Mm-hmm. I'll go on tour. Oh. Dreams shattered. Unfortunately, I can't get out of like the kids song version. It's like, for each unit of x, we increase by the slope. No, I don't know. For each unit increase, don't quit your day job. I should make that an assignment, actually. Everyone has to write a song. I'll perform it. Yeah. You'll never forget it. If you write a whole song about it, you'll never forget it. For each unit increase in x, we expect, I know, so boring. In x, we expect b1, right, which is the slope, unit increase in y hat, which is the predicted value of y. Right. Okay, let me see here. No, not yet. Get carried away. So, bare bones, this is the interpretation of the slope. And so for each unit increase in x, we expect to see a b1 unit increase in y hat. I use increase always, right? Even if I have a negative slope, a negative increase is a decrease, right? You want to be really careful with using decrease, because then if you have a negative slope and you tell me it's a decrease, then a negative decrease is an increase. But if you always just hold steady with the increase, it's going to sound weird, and you can adjust it once you're comfortable. But I always just say increase, even if it's negative, right? And so then, because a negative increase is a decrease, right? So you don't want to get too fancy here, not yet. Obviously, if you're reporting to, I don't know, the city or something, maybe change it, right? Maybe take a step back and think about, okay, if I have a negative increase, then that is, you drop the negative and a decrease. But for us here, we're just learning. Okay. And you can kind of, the more you stare at this, this equation, you can kind of get to this interpretation by by just kind of using the line. And that's hard. And yes, my dad used to say, well, just squint at it for math problems. And so that's kind of and it works. Just squint at it. Crying. No. For the intercept, slightly easier interpretation. If you want to relate, and just like we did here, we related the slope to the y hat, right? And so how do you relate your b naught to your y hat? Well, it's going to be the predicted value of y when x is 0, right? Thinking about the y-intercept, that's where x is 0, right? And so that's what we incorporate into our interpretation. And so b naught is the predicted value of y. I'll use y hat for shorthand. But when you see y hat on its own, you just read it as the predicted value of y. Okay. Is the predicted value of y when x is 0. There are many scenarios where x being 0 makes no sense. Right? And so, but it is still the interpretation, right? But if it doesn't make sense, then you would probably add that, right? This is just, it doesn't make sense to consider the intercept on its own. Okay? So there are many relationships where x equals 0 is meaningless. Just end it there. It's still the y-intercept, right? Lines keep going and keep going and keep going. Negative infinity, positive infinity. That's the beauty of lines. And at some point, they will cross the y-axis, right? But whether it's meaningful or not, right, that's going to relate back to, well, can x be 0? Do I care about x being 0? Right? Okay. Now, I'm going to go back and hunt down, because I know it's in here somewhere. Please stay on the line. I hope. Maybe they just gave us a fake line. As an example, I'll put it on the next page. For the possum data, we might find this, that y hat is 41 plus 0.59 times x. I say might because they just decided to pick a line. I don't like that, but I can't find the real one. So let's just say that this is it. We can rewrite this if you want by ding, 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 ding. By replacing your y with the head length and your x with the total length. We do that kind of often as a way of making the equation easier to read. this over here. So we might write y, which is the head length. Throw a hat on there. I did kind of a stylistic hat. It's okay. Is 41 plus 0.59 times the total length. Now it makes it more obvious that these are just placeholders for some total length, and in return, I'm going to get some predicted head length. And so now, our next job, if we have this equation, is going to be, okay, well, how do I interpret these things, right? How do I interpret this equation? And so you're going to start with the slope, I think, is probably the best way to do it, although I guess it doesn't matter. Interpret the line. Usually I break it up and say interpret the slope and then interpret the intercept. Right? And so, fine, I'll do that. Fine. Interpret the slope. I see the slope is 0.59. Okay. But I also want to interpret it in terms of x, which is, in this case, the total length, right? And my predicted value of y is the predicted head length. And so now, from this generic interpretation, right, I'm going to replace all these things with the question-specific variable names, right, and values. So for each unit increase in total length, we expect a 0.59 unit increase in the predicted head length, right? And so let's do that. For each unit increase, and the unit increase is important, right? You can't just say for each increase in x, because that's not specific enough, right? You want to say unit increase. So for each unit increase in total length, we expect a 0.59 unit increase in the predicted head length. That's something you can report to, I don't know, whatever stakeholders you have, right? Whoever's making you make the report, me in this case, right? But that's kind of easier to communicate, right? How about if you have to interpret the intercept? What was the intercept? The intercept was the predicted value of y when x is 0, right? I guess I can go up there, right? The intercept is the predicted value of y when x is 0. So 41 is the predicted head length you can say when the total length is 0, but it might be a little bit better to say for a possum with a total length of 0. Right? But I'll keep it nice and simple for this one. But you can kind of start adding some flair to it. 41 is the predicted head length when the total length is 0. that meaningful information? Not really. I really hope that if the total length is 0, that there is no head length because yikes, I don't want that. No, thank you. And so I don't want that. Okay. This is not meaningful. Since the total length can't be 0, right? You want to relate it back to 0 or the x being 0. This is not meaningful since the total length can't be 0. Which brings me to my next thing. What we did here was called an extrapolation. Right? And so you're using the line, and like we said, these lines keep going and going forever, right? Both directions. That's the beauty of them, but they're only useful for the range of your x's that you built it on, right? And so here, when we use the line to predict outside the range of our x's, we are extrapolating. We are extrapolating. And so one thing that you could do if you're kind of arguing with yourself, okay, can the total length be 0? That one's pretty obvious. Sometimes we don't have any understanding of our data and we're just kind of flying blind. So then what you want to do is you want to look at your scatter plot that you built this line from. This line is really only useful in this stretch, 75 to 95-ish. And so, of course, the line keeps going and going and going. Right? And we can still, if we're not careful, we can still make predictions outside this range, right? But here, the line is only reliable, right, in this stretch of x's. In this stretch of x's. All the x's in our data. Okay. So you might have to extrapolate. There are scenarios where you have to extrapolate, and it is still your best guess, right? But just be aware that you have these unreliable predictions. And so we can extrapolate, and it is still our best prediction. And it is still our best prediction. But it is not a reliable prediction. Extrapolation is one of those things where you see it a lot in kind of the news and stuff where they've tried to extend lines, and there's lots of different examples where they're making all these crazy predictions, but they're extrapolating way beyond the data, and so making it unreliable. But then they're using it to make headlines, which is not cool. So now you keep an eye out for that. Send them my way. I don't have any up my sleeve right now. I can hunt some down. Okay, let's see here. So we've got a line. We know how to interpret the slope, the intercept. The last thing that we usually incorporate is on top of our line of best fit, maybe y hat is 41 plus u plus 0.59 times x. Right. In Excel, you've made a scatter plot. You can add the trend line, tell it to put the equation on the graph. That's nice. And usually what we do is we also add the r squared, right? Yeah, the r squared is kind of the most common way to determine how well a line fits the data. And so r squared, what's it called? The coefficient of determination. I just call it r squared. The r squared is a measure of, oh, sorry. Thanks, Steph. Is a measure of how well our line fits our data. Of how well our line fits our data. What's cute is the r squared is the correlation squared. So r squared is the correlation squared. Just kind of grows up when you square it, I guess, becomes a capital R. So it is the correlation squared. And the correlation goes between -1 and 1, right? And so if you square a value between -1 and 1, you get a value between 0 and 1, right? Just kind of flops itself onto the positive axis. And now this r squared is a value between 0 and 1 then. If I take a small value and I square it, or a negative value, just kind of stays in the 0, 1 scale, which means what? It means it's a proportion, or we usually report it as a percentage. Yeah. And so r squared is technically between 0 and 1. Yeah. R squared is a value between 0 and 1, usually reported as a percentage. Oh no, that means I don't have much time. Start the clock. I have so much to say. So the r squared, in most fields, you'll talk about the r squared. Okay? And if the correlation is baked in here, then a high value of the correlation is going to be reflected in a high value of r squared. And so what you're striving for is as high of an r squared as possible. Okay? And so the goal is to achieve a high r squared. when we're modeling and we're comparing different relationships and different scatter plots and things like that and different models, one of the things that you would do is you would compare the R-squareds, right? And then you would use the one with the highest R-squared, right? That's the motivation behind the R-squared, is it gives you kind of a metric, right, that you can use to compare different models, right? And so here, the R-squared is a metric used to compare models. Even people who are not in stats, but just kind of doing research and writing reports, they'll talk about R-squared a lot. But I bet you they couldn't tell you what the definition of the R-squared is. So the definition of the R-squared is this. It's the percentage or the proportion, right? Because any value between 0 and 1 can be considered a proportion, right? And if I multiply it by 100, I get a percentage, right? And so you can use those two interchangeably. Let me write that here, right? Between 0 and 1 is a proportion. And then, but usually a percentage, which means that they're the same. You can use them interchangeably, right? And so R-squared is the percentage, right, or proportion, but usually in your report, you're going to talk about percentages. Okay? And so R-squared is the percentage of the variability in Y explained by the least squares regression line on X. We don't get a lot of time for me to harp on this, right? But what I do want you to start building in is, as soon as you see something about the percentage or proportion of variability, right? So if I ask you, hey, what's the percentage of variability? And then you stop reading because it's so long in the predicted or in the head lengths explained by the least squares regression line on the total length, right, is what it would say. You should just think, oh, percentage of variability, I know what that is. That's R-squared, right? Just kind of have that connection. And for now, right, just kind of set that trigger. Percentage of variability, R-squared. And then because we have to talk about it properly, of course, I'll include the rest, but you can kind of stop reading at that point. And so, how's that? If we were doing a regression course, right, of course, I would make you memorize it. But there's enough memorizing. Okay. So if we have the correlation, and let me see, let's say that the correlation here, let's pretend, is what? 0.75. I don't know. Seems reasonable. So for example, say R is 0.75. Positive because I can see it's a positive relationship, and 0.75 because that's pretty strong, right? They're not all on the same line, but they're kind of hovering around the line, and I can see a relationship here, right? Kind of nice and, hey, where's my pointer? There, nice and tight, right? And so pick 0.75, 0.8, anything like that. So now the question would say, find the percentage of variability in head lengths explained by the least squares regression line. Oops. Least squares regression line on total lengths. Which means find R squared, right? See that percentage of variability here? Boom, stop reading. Well, maybe confirm. So what I want you to do then is your R squared is your correlation squared. Which means it's 0.75 squared, which is what? Does anyone have it? Thank you. 0.5625. Small numbers, when you square them, don't behave the way you want them to. They get smaller. All right. Okay. So now the percentage of variability in head lengths explained by the least squares regression line on the total lengths is 56.25%. As a percentage. The flip way, right? We need the correlation to find the slope, right? And so another way that I could do it is I could give you the R squared, right? If I give you the R squared, and you have to calculate the correlation, right? And one of the things that you want to remember is that by squaring it, you lose the negative, right? That was the whole point. But when I undo the square, when I take the square root, I get a positive and a negative result, right? And so then you need to look at your relationship and use the positive sign if it's a positive relationship and a negative sign if it's a negative relationship, right? And so we can find the correlation given R squared, right? The correlation is the square root of R squared, but it's the plus minus square root of R squared, right? Just to bring it back to unfold it onto the negative side as well. And so here, pick the sign, right, from the relationship in the scatter plot, right? If you have a positive relationship, you keep it positive, and if it's negative, you have to attach the negative. Pick the sign from the relationship in the scatter plot. So that's just a heads up moving between those two. I'll move this there. Okay. Nice. let's look at, she does talk a lot more about residuals. Another way that we can compare models is by what we call a residual plot. And so you have the original plot here, and then you have your residuals against the predicted values kind of down below. We'll see if we get into residual plots. I'm going to parking lot them for now, but they are an additional thing. If you're building a lot of models, then you'll read about residual plots and how to use them. But it really just kind of, the goal of a residual plot, maybe I'll add that, is just to magnify the relationship in the original scatter plot. So here you can see, okay, there's probably some curvature there, and maybe this line isn't doing a good job. And so then it's just kind of magnified in the residual plots. Okay? And so that's the only thing that I need you to know about residual plots for here. A note about residual plots. They are a really common tool. A residual plot plots the residuals on the y-axis, plots the residuals on the y-axis, and there's different techniques. This textbook, she plots the predicted values on the x-axis. I sometimes use just the x value, right? You can use the y value. So there are different techniques, but and the y-hats on the x-axis and it magnifies the relationship in the original scatter plot. And it magnifies the relationship in the original scatter plot. So here, this is what we call, this is the original and then this is the residual plot. A residual plot. We usually have a line at 0, right? Our residuals should be hovering around 0, right? We want our points close to our line, right? And so here we see that it magnifies this non-linear relationship. But for us, in a residual plot, we look for even random scatter around 0. Anything else is kind of evidence against an ill-fitting line. And so in a residual plot, we look for even random scatter around 0, which is here at this dashed line. Otherwise, we have evidence against this, or just kind of an ill-fitting line. Otherwise, we have an ill-fitting line. So once you build all your models, usually when you're modeling, you would build a ton of different models. You would compare them, compare the R-squareds, compare the residual plots, right? Do the same thing over and over and over again until you land on one model that you're ready to publish. right? And so you land on not the best model, but there are often trade-offs. So, but that's not for us. Right? But if you do have to deal with residual plots, you can come see me, but I think probably not. You'll use the R squared, like most people do. There is an example that I want to steal. Here, I guess I could include the description. It's already got a line on it. So we can see that it's negative, right? But as a jumping off point, so here we have the gift aid. And so gift aid is just money that you don't have to repay, I guess, from the university. That'd be nice. Huh? So you get some gift aid in some amount, but it depends on your family income, right? And so for a random sample of 50 first-year students from Elmhurst College. And so here we see that there's a negative relationship. And if we had to describe this relationship, I would describe it as a moderately strong. I mean, I see a pattern here. There's some variability, but around the line, right? But I see a pattern, and so let's say moderately strong, negative linear relationship. Moderately strong, negative linear relationship. There's no other shape than a line that I would use to describe this relationship, right? And that's a good thing because we're about to fit a straight line to it. Let's see if we get the they didn't give us the correlation, or at least not that I can see. But the thing I wanted to bring in earlier that I couldn't find for the possum data is in software, we usually get some output like this. And so using, I'll say generically software, you should use software. Right, we don't actually do it by hand. So using software, we get the regression output. Where we're going to focus is here. Later, we might be able to kind of incorporate the rest of the table, but for now, all we need to be able to do is read this table and what does it look like? So I have an intercept. That's kind of telling, right? Then maybe my intercept is 24.32 for my line, right? And then I have the family income, but I also happen to know that family income is on my x-axis, right? And so the multiplier of family income is my slope. And in this case, my slope is negative 0.04. So from here, this means that B0 is 24.32 and B1 is negative 0.04. So from this, generically, we can say y hat is 24 point, or let's do the bare bones one first. B0 plus B1 times x. So y hat is 24.32 plus negative how about I just switch it to minus 0.04 times x? Or in words, let's say this, the y-axis is the gift aid, right? So the predicted gift aid, or gift aid with a hat on top. Oops. My hats don't look very good. The predicted gift aid is 24.32 minus 0.04 times the family income. You can interpret the slope. You can interpret the intercept. Interpret the slope. Now this is in thousands. I'm pretty sure. But let's just ignore units for now. So interpreting the slope, I have a slope of negative 0.04. We didn't even have to do any calculations. That's nice. And so what's the interpretation of the slope for each unit increase in x? So for each unit increase in family income, we expect a negative 0.04 unit increase. Just to illustrate what I was talking about earlier, we expect a negative 0.04 unit increase, or if you prefer, this is a 0.04 unit decrease. But you have to be really careful that you drop that negative, right? Otherwise, it's wrong. So we expect a negative 0.04 unit increase. Right? With time, you can kind of take those training wheels off, but you don't need to. In the predicted gift aid. What if we had to interpret the intercept? The predicted gift aid is 24.32 with the family income of 0. I'm going to try to keep it on this same page here, but it's tight. Can't really buy any room anywhere. Try to smush it before I post it. Interpret the intercept. The predicted gift aid for a student with family income of 0 is 24.32, and that's in $1,000. Nice. Good job, guys. If you have any questions, let me know. Otherwise, whoa, wait, when do I see you next? Tuesday. Well, I'll miss you. Enjoy your weekend. See you. Hello.